So, good morning, everyone. Today we have Professor Chen Yuxun coming here to give us a seminar talk, and our partner, Professor Yong Chen, right now is online. And Professor Chen Yuxun is the researcher working on mechanism design. She has a really unique research topic. I'm not sure if she will talk about it today, but she probably is one of the very few researchers who works on history of mechanism. And some of her colleagues will try to look into ancient mechanisms which has no documentation mentioning what's the design and details about the mechanism. You only see them maybe from some historical document, some pictures, or real ancient mechanism designs. So she and her colleagues tries to discover the real design from those ancient mechanisms and try to maybe analyze why those designs were made many years ago. And I think she can tell more about this kind of research later on. So I will give the time to Professor Chen Yuxun. So let's welcome her.
Okay, good morning, everyone. Okay, to the United States, I think that is good evening. Okay, so I'm really glad that I got this opportunity to share the experience about the research, but it's mainly about mechanism design, and also thanks to Professor Li's introduction. Today our topic is creative mechanism design methodology and its application. Well, basically we talk about a methodology that is a method to help us to generate the mechanism structure. However, I think I know the most charming word is creative, but I would like to start the word mechanism. Okay, so before we start this lecture, I would like to define what kind of mechanism we talk about over here. Okay, so what is a mechanism and what's different between mechanism and machines? That is, we said generally we define the mechanism is composed by the rigid members, and also the members have to be joined together to generate the function. Also, for some specific task, for example, if we have a robotic task or some specific task, we most generally we decide a path, or we decide maybe the position, we decide the velocity, or sometimes we decide the specific maybe force or moment we have to generate. And what is a mechanism? We say it is combined by links, or we say kinetic members and joints. So what kind of mechanism we use every day? For example, the door. Okay, there is two links, the door and the wall, and then they join together by the hinge. That is, we say that is, we define that is a revolute joint. And then how about the window? Here is a window and a wall, and also two links. Over here, that is a sliding joint to make the specific motion. Well, when I was an undergraduate student, my teacher taught us the example is the flip mobile, the mobile phone, and the slip mobile phone. However, I'm quite not sure how old are you. Okay, have you ever seen this kind of mobile? Well, I think for professor, I believe you haven't ever used this kind of mobile. But how about the sliding mobile? It's real, right? At that time, I think that is the other strange design that is it rotate along the other axis. I think it's made by Sony. At that time, maybe Sony Ericsson. And however, there's the other side. We define there are two links and combine it, and there is a joint, combine them together, and also two members, and combine them by the sliding joint. So that is the definition of a mechanism and machines. What is a machine? If we say a car is a machine, and what mechanism is included, such as if we have a whipper, if we have the vacuum wheel, and some, or we have that, some like the engine. As we know, there is a piston, cylinder, and we have the crank to drive all of the car. So that is a machine and include many mechanisms inside. And okay, we will talk a little bit about the historical things. I think that is they provide an example for us what kind of mechanism we are talking about. That is the first example. In the mid, I think in the 1st century, Alexandria area is located at Egypt. Well, what is this design? As we know, that is the door of the temple, and that is fire lit. So I think that is a ceremony, like if that is a king, and they have to prove that they got the power. Maybe that is a god, that the god is authorized, that is this guy, that he is qualified to lord everyone. So the king, they will go there and to fire over here, and then a moment later, if the door of the temple open up, that is a proof of the authorized by God. But how? How could we generate this motion? One of the students told me it's easy. We just put the thermal sensor over here, and then we put the servo motor. Okay, so once the sensor it detects the temperature increase, and then it opens the door. Well, that's feasible, I know, but that is in the 1st century, without electric components, without any electric control. So how could we generate this kind of design? I would like to remove this part to show you how people design that at the time. That is, there is a content. In the beginning, it's full of water. Once the temperature increased, the volume of the air that will increase, and then the water will be pulled outside to the basket, and then there is a weight. Once the weight increased, and then there is a weight. Once the basket is heavier than the weight, and then the basket moves downward, and then what will happen? Here is a chance, and they wrap it around the pillow. So once the basket moves downward, and the pillow, they will rotate to open up the door of the temple. So I think that is a classical. We say this classical design at the time to prove what kind of science and technology they have already known. For example, they have already got the sense how about the volume of the air and the water. They share the space. So that they can design the device in this way. And then they also know how about the weight. They also got a sense the heavier thing will fall down. And that is a design at the 1st century. We say, oh, what kind of mechanism components have been used over here? We can see that there is a pulley, there is a chain, and also okay, over there is another pulley. And over here, they also use the revolute joint. You can see the design at the time of the revolute joint. Although they don't have the bearing, but they have already know how can they decrease the friction force when their components rotate. Okay, so that is our first example about mechanism design in the first century. And then we provide maybe more example. Okay, for example, like this one, the other Egypt's water wheel. Okay, so here we can see how about the power source? That is a camel. And then there is a pair of gear over here. Here we have many baskets around this wheel. So once the camel it moves forward, and then the basket will deliver the water from the underground, deliver the undergrounded water. And how about this one? This is for the grill. Okay, I think maybe last month in Taiwan, almost everyone have the barbecue in the Moon Festival, and that is one of the design like that. So we can see that over here that is a meat, and then once it is heating up, the hot air moves upward, and here is a fan. Here we have a pair of gear, the other gears, and then the gears. So we can see how about the performance, how about the result? That is, with the hot air move upward and the fan start to rotate with the transmission by the gears, and then your meat will also rotate automatically. Okay, so that is what we call that is mechanism sims. Over here we use the components like gears. We also and also we see the other kind of design. How did they generate revolute joints? At that time, I think that is maybe 15th or 16th century. We still don't have the bearing. That is one more interesting example. So what is that? That is perpetuum mobile. That is, at that time, people believed that if we have a machine and we put a tank of water over here, once the water flow downward, and they will make the wheel, the water will start to rotate. And then there is a screw. Okay, so with the transmission from here, the gears and the other pair of gears. Once the water will rotate, the screw will deliver the water upward back to the tank. And then people believe that this device they can work forever. They won't stop. But as we know, it's impossible. Okay, so at that time, people still imagine that whether or not we can generate the power source, and if that is possible, the power generated is free because the water can be used recycling again and again. Okay, so over here we see more mechanism components applied it. So, okay, let's go to our lecture today. So the outline is, at first we will have an introduction about the creative mechanism design methodology. So as an example for the mechanism designs we have already seen, what is the most difficult part? Let's look backward. If today we got a task, if we have to do something like this one, okay, what is the most difficult part? You think about that? Generally, the most hard part is which component should we use? How about the mechanism? How about mechanism structure? Over here we can see that it is something like they use pulley, but there are some maybe that is the key that they know. They know that the heat, if we make the air heating up, the volume will increase. And also they they make the space arrangement about all of the components. So the first thing is, which type of the link should we use? Should we use a pair of gear? Should we use linkage or pulley? So, and then how can we arrange all of the mechanical components together to generate the motion we want? So the most difficult thing generally that is the mechanism structure synthesis. Okay, so this methodology we will introduce today, that the scope of use that is to generate the mechanism structure. And at first, we will make a briefly introduction for this methodology, and then we will take a brief review of the basic concept of mechanical device. I think if you have already got a degree in the Department of Mechanical Engineering, you must took a course net mechanism something, right? Generally that is, but I believe maybe you don't remember all of the detail. So today we will make a brief review, especially for the degrees of freedom part. And then we will also show you some mechanism diagram and the kinematics chance. There is a quick review. And then we will go to the design procedure, that how can we generate a new mechanism design structure. And there are 3 steps, and then we provide many design examples. So at first, how do we generate a creative idea? Sometimes we just think something, but generally, that is a step-by-step process, right? We get the idea, and generally that is based on something. Maybe we have maybe we refer to the existing design, or maybe we find something with the same kind of machine that generates the path, but that generates the path we want, but presently that it's used to the other area, the other usage. So generally we get the creative idea based on something that existed, right? So that is how, and how about the mechanism? As we know, we just take a historical review, and we find that most of the mechanical parts have already used for really long time, right? Maybe thousands years ago. So I think it's especially for the mechanism, okay, it is developed step by step. And then how about the scope of use? Here is the whole procedure for the machine design, from the first problem definition to the last, that is the analysis for static, like the material, the materials, and then the dynamics. But for the mechanism design, generally that is the first 4 step, problem definition, and how could we generate a mechanism structure. Then it's a dimensional synthesis and the motion analysis. Okay. Here we provide an example. That is a suspension. Okay. Here is a suspension mechanism for the motocross. Over here we can see that it's a shock absorber. And if you got the experience to ride in a scooter or motorcycle, I think that is that is important for your experience, whether or not it's comfortable. If we got a shock absorber is too hard or too soft, okay, I think the experience will not good. But how can we generate a mechanism like that is defined in which angle over here it connects to the rear wheel of the motorcycle, and that is a swim arm. It's defined the curve that at which position they should compress the shock absorber, maybe a displacement is defined. But how could we make the relationship between these two? The input is the rotating angle of the swim arm. The output should be the compress to the shock absorber. And that is a 6-bar linkage. It's widely used in the motocross. But how could we generate the mechanism structure? So if we think about the methodology, if that is a black box, the input should be the existing design. So that is a product by Suzuki. Okay, so now we can find the existing design. Okay, and then we analyze the design. What kind of characteristic over here? That is, we find, okay, that is a mechanism structure. And we find that there is 6 link and 7 joint included in this mechanism. And then it's required, we need a shock absorber over here. And a shock absorber is composed by a piston and cylinder. So there are 2 links. And then we need a frame that is a fixed link for every mechanism. And then we need a swim arm over here to connect the mechanism to the wheel. And then we still need some connecting links to generate all of the mechanism. And that is the characteristic we analyzed. So if we made them as an input to the methodology, what is the output? The output is we can generate other feasible mechanism with the same function. Okay, so we input one design, and then we can generate, over here is 10 mechanism designs, and all of them are feasible. So, but why? But why? That is, okay, the yellow one that is the original design from Suzuki. We still find the green one that is we still can find the green one at the existing design that is made by Kawasaki. And the red one from Honda. This 3 design that is published at about the same year. Okay, we are quite not sure whether or not they refer to each other, but these three brands, they use a different design for their rear suspension. And how about the other 7? They are the novel design, right? So if we have already got the mechanism and we know they can generate the function, why do we still need new designs? Whether can us use the existing design directly? Generally, no, because there is something that patent, right? If they have already applied to the patent, okay. So that is the reason why we still need a new mechanism. We still need the mechanism structure to avoid sometimes it's about like the strategy to protect your design, or that is we can avoid the patent have already been applied it. And then let's take a brief review about the basic concept of mechanism analysis. So as we mentioned, a mechanism is composed by a link, by many links and many joints. But in this methodology, we make a representation like if you find a capital K with subtract something, that means a link. Okay, that is the symbol of the link. So over here you can see all kind of link, they are represented by the capital K, by K something. And for the joint, that is capital J something. Over here we also provide 2 examples to show you what kind of the mechanism components we use over here. Okay, so that is, do you see the gears? The gears, yes, that is a kind of component we use, that is kind of link. And then do you see the linkage? Here is a kinematic linkage. Okay, so this, I think over here is not all of the mechanism part, but that is maybe the most widely used mechanism part over here. And here, the other one is familiar, okay? Over here, we still can see the linkage. We can say, oh, this automata, that is make the generation, they generate the motion by a linkage mechanism. And then that is a joint. Here is a table for the joint. We represent it by J something. Just like we just mentioned, for the door, generally that is a revolute joint. And for the windows, maybe that is a sliding joint. We still have the other kind of joint, like we have a gear joint, we have the cam joint, and other kind of joint. For example, like a spherical joint. That is like our shoulder, a joint of our shoulder, that if we can rotate our shoulder maybe to move forward, to make upward, and maybe it can rotate along x-axis. So we say that it's 3 degrees of freedom. That is, you can rotate along 3 directions. And then we defined 3 degrees of freedom over here. And how about the revolute joint? Only 1 degree of freedom. Think about that. How could we operate the door? To rotate it along the axis of the hinge, right? Only 1 degree of freedom. And still the same, the sliding joint. Okay, that is maybe 1 axis we can make it move. So that we defined it as 1 degree of freedom. And what is the most important thing in this table? That is, here we list the degrees of freedom for all of the joints. And then once we combine the mechanism together, we can find the degrees of freedom for the whole mechanism. And I believe you have ever learned that, maybe if you have ever took the course of mechanisms. So over here, for example, like for the planar mechanism, okay, here is a simple equation that we can calculate how about the total degrees of freedom for the mechanisms after we combine all of the after we assembly of the link and joint together. Okay, so what parameter is important, like the number of links, number of joint, and which joint we use, and how about the degrees of constraint of each joint. They are the parameter that we have to consider, and then we can determine the whole degrees of freedom for the mechanism. Okay, so, and then I will open up the black box. So if here is a methodology, and here we can list all of the steps. At first, we have the existing design, and we make the characteristic analysis. So, for example, this is an example we just saw that, the Suzuki motocross, and we analyze the rear suspension. So, what kind of existing design generally we search? For example, like the product in the market, maybe the patents, and sometimes we also survey the literature, like the published paper or the other kind of designs. Okay, and once we get the existing design, here the characteristic will be analysis. What is a characteristic for the mechanism? Generally, the number of link and joint, and then what kind of link and what kind of joint. So in this case, all of the joints, so over here we can see between the piston and cylinder, there is a sliding joint. Both of the two components generate a shock absorber. So the sliding joint over here is required. But for the other joint, there are six revolute joints included in this mechanism. So that is what we say that is characteristic. And then there are some components they are also required. For example, we need the fixed frame. We need the swing arm to connect the wheel. We need the shock absorber, include the piston and cylinder. So they are the important, we can say they are the rules of the links. They are required to generate the function. And then let's go to the next step. That is the generalization. What is generalized? It is something we say it is generalized. That means in this step, we will remove the features of the mechanism. What is the feature of a mechanism? That is, for example, we just introduced many kind of links and joints, right? So what about the generalization? That is, no matter originally what kind of link and what kind of joint is applied it. In this step, we will make it to the most general one. So what is the most general link? That is a kinematic link. And then, what is the most general joint? That is a revolute joint. Okay, that is, you just follow the definition. So, for example, over here, that is a pair of gear. Okay, there are 3 gears engaged with each other. Okay, so here we can see that, okay, if we name the fixed friend is link number 1. Link number 2, 3, and 4 are 3 gears. And we can see link 2 and 3, they engage each other. 3 and 4, they also engage with each other. How can we make the generalize? How can we remove the feature for this gear mechanism? And over here, only 2 things we have to remember. At first, the adjacency relationship has to be kept. That means if originally link 1 and link 2 are connected with each other, they will have to keep this relationship. So think about that. How about link 3? How many neighborhoods for link 3? Link 3 is connected to link 2, link 4, and also link 1, right? So we say there are three neighborhoods for link 3. And then once we remove the feature of gear, and it will become a link. The link still has 3 joints, because originally here is a gear with 3 joints with each other, right? We have 3 joints for link 3. So over here for link 3, there are still 3 joints over here. And how about gear number 2? Originally it connects to the frame and also connect to link number 3. There are 2 neighborhoods. So once it removes the feature, it also have there is a link with 2 joints. Okay, so that is a relationship of adjacency we have to keep before and after the generalization. And then let's move on. So now we remove the feature of gears, and then how about the other feature? The frame, the fixed link is also a feature. How can we remove it? Here that is still a link with 3 joints, right? So they will become the other link with also 3 joints. Okay, that is a rule for the generalization. So that is, once we remove the feature of the gear mechanism from here, and it becomes the generalized chain. However, the adjacency relationship is kept. That we can see link 2 and link 4, originally they don't connect to each other. And how about that in the generalized chain? Link 2 and link 4, they still don't connect to each other. Okay, so that is a relationship we have to keep. And one more thing, the total degrees of freedom should be the same. So for example, as the definition, here as a definition, over here we have two gear pairs, we have two gear joints. And as we a definition, the gear joint has 2 degrees of freedom. And then it can become, here, if that is 2 degrees of freedom, they can become one more link with two joints that with a single degrees of freedom. However, the total degrees of freedom should be the same. Okay, that is the 2 rules for the generalization. Okay, so that we can make the gear mechanism with become the generalized chain over here. And something interesting that is, if we provide more example, like here we have two more mechanisms. That is, this one is two, both of them are strange mechanism. For example, over here we have a roller, we have a cam, and also the piston and cylinder. For this one, we have a pulley and rope, a slider, and springs. However, if we make generalization for both of them, the result are all the same. Okay, if we remove all the feature for the 2 mechanisms provided, the result, these 3 mechanisms after generalization, they are all the same. Okay, so it's just like we can find the same DNA with maybe like human beings. So that is what kind of DNA will generate, if they generate together, they will become maybe the human beings, but maybe different experience, different features. However, if we source back to the generalized chain, we can find a different mechanism with the same generalized chain. Okay, so that is the step for generalization. And let's implement this step to our example, that is the Suzuki rear suspension. So we can see that, if we apply that to this example, for the rear suspension, there are six link and 7 joints. So we can make it from here to here. Take a look at, for example, like link number 2. Originally, that is a link with 3 joints. And after generalization, it's still a link with three joints. And then link 2 with they are the neighborhood for link 2. That's link number 5, number 1, and number 4. And after generalization for link number 2, his neighborhood is still links number 1, 4, and 5. So we keep the adjacency relationship before and after the generalization. And why we have to do that? Why we make the generalization? That is, they just like a database of the mechanism DNA, that we can have an atlas of the generalized chain. That is basically that is based on the mathematics about how could we. That's about the just like if today if we take for example, if we take 2 triangle and 4 bar, how many types of the generalized chain can we assemble? So over here we find a result, that is 3 results that we can generate with the same components, but they are the different methods to assembly them together. Okay, so that is what we call that is a generalized chain, and that the database is from the mathematics, and then once we find for example, the mechanism with 3 links and 7 joints, they are only 3 atlas of the generalized chain, and then we can develop our new mechanism based on these generalized chains. So let's move on. Number synthesis is a method. How could we generate all of the atlas? And then here we have the design requirement and constraints as we analyze. with 7 links and 6 links and 7 joints. And over here we find that it's all of the feasible atlas with the number of links and joints. And then we need a Shaka solver. Both the piston and cylinder should be the link with only 2 joints. And then we had other 3 types of links. So let's start to the next step, that is a spatialization. Okay, at the previous step in generalization, we removed the feature. But over here in the step of spatialization, we have to put the feature back to the generalized chain. So over here, we start at this 3. And the first thing we find in this atlas, here is the 3-bar loop. And in the mechanism, it will become a structure. They cannot move with each other. So at first, we remove this atlas. And then we still have 2 atlas of a generalized chain. So let's start to assign the role back to the generalized chain. So over here, if we have the frame that is a fixed link, there are only two results if we assign that. That is, we could assign that to the link with 3 joints, and then the other option is to assign that to the link with two joints. So over here we generate 2 different results, and this is still the same. For this generalized chain, that is 3 results. That is 3 possible results to assign the fixed link. For example, that is, if we assign the link to this triangle or to this triangle, will become the same result. So we just keep one of that. And still the same for these two links, we can say they are the same rule for the mechanism. So we just keep one of the result. And then to generate, one more result can be generated. That is, if we assign the frame at a link over here. So in this atlas, we get 3 results that is a specialized chain with fixed links. And still the same, just put it back. How about the piston and cylinder? They have, it is required to make both of them. They are the links with 2 joints, and then they have to connect with each other, or it cannot function. So how about this? How about this one? We can assign it. These 2 links, we can say they are the piston and cylinder to generate the Shaka solver, and over here is still the same. Okay, so with the familiar process, over here we get 5 results with the fixed link and piston and cylinder. And next, and then we find over here, okay, this one maybe is not feasible because once we put the frame over here and we cannot find the other 2 binary link and connect it to each other to serve the role as the piston and cylinder. So over here, this result cannot generate the feasible result. Okay. And then let's move on. How about the swing arms? So over here, we can generate the swing arm. We represent it by KLS. So over here, we can put it like over here, over here, and over here. Okay, I think it's 3 results that we can put the KLS. And then we list the result over here. Okay, and then how about this one? If the link still don't have the rule, we can assign a role to him if we say, okay, so if here is a fixed link, here is a Shaka solver, and how about this one to serve as the swing arm? So there's still 3 results we can generate it based on this specialized chain. And over here we have already got 6 results, and for these 2 specialized chain, they are the other 4 results. So the other links, if they still don't have any role, we can assign them to serve as a connecting links. So finally we get 10 spatialized chain. Okay, and that is the step we say spatialization. That is, we can assign the feature back to the generalized chain. Okay, so then we have the final step, that is particularization. I think that maybe that is the most difficult step in this methodology. How about the particularization? We have to make the spatialized chain. We have to draw it back to the mechanism gauge. How? Let's take a look at maybe one of that. For example, this one. Over here, I still list all of the representations of symbol, like KF is a frame. So let's take a look. How about the frame in this spatialized chain? Over here, the frame is the binary link. Okay, so once we put it back to the mechanism, the fixed link, yes, that is a binary link, only 2 joins, and it connects to connecting link. Okay, so here we have the fixed link. It connects to the 2 connecting link, and take a look over here. These 2 connecting link, KLC and KLP. Both of them, they are ternary link. So over here in the spatialized chain, they are triangles. And the after particularization, okay, over here, the 2 connecting link, they are still triangles. And Shaka-Sober link 5 and 6, they will put that between these 2 connecting link. Yes, that is. So the relationship of adjacency of the spatialized chain and the mechanism gauge are still the same. So that is the reason why once we complete assigning the role of the links, and then we can generate different mechanism. Okay, and we can still find that this one is the original design, but the other 9 physical mechanisms, they are the novel design for the real suspension mechanism. Okay, so it take a long time, but I think that is the main part. That how could we how about the creative mechanism design methodology? That is, they tell us how could we generate the mechanism concept, the mechanism structure. That is not, we cannot wait, or maybe we can generate an idea, right? But in this methodology, tell us that is a systematically process. At the first step, to deal with the analysis of the characteristic. Second step, generalization. The third step may be the specialization, and finally, we can draw it back to the mechanism gauge. Okay, so that is, once we have the deadline and we have to generate a new concept, that is a useful methodology to help us. And over here, we also can provide many examples. So maybe briefly, 2 examples. Like this is a clamp device. Originally, that is this device. Like we can clamp the workpiece. And after the black box of the methodology, we can generate 10 different mechanism structure of the clamping device. And how about this one? That is the breaker. Okay, that is a breaker switch. And originally 1 design, and finally we can generate 7 designs with same function, but they are all with the different mechanism structure. And if we have to apply the new patent, that is also useful method to help us generate the new idea. Okay, so because of the time limitation, any questions?
Any questions from the students? Yeah. Okay.
Professor Chen, I have a quick question.
Yeah, sure.
So, I get a little confused because you show gear joint has a 2 degree of freedom.
Yes.
Why there are 2 degree of freedom?
Okay. I think that is a result that we can determine that. For example, well, let me show you an example. Like we have a pair of gears. For example, this one.
Right.
Consider that if presently we don't have gear 4 with the fixed link, gear 2 and gear 3, they can rotate, right? They can work.
Right.
Yes.
There's only 1 degree of freedom you can rotate, right?
Yeah. So how can we generate the result? The equation is defined like for the planar mechanism. Can you look at can you see the equation I
Yeah.
write? Okay.
Let's go to the.
Okay. So, go from. Okay, this part. Okay. So, because that is a planar mechanism, the maximum degrees of freedom is 3. And over here, if we have 2 gears only, so we have link 1, 2, and 3. So now we have the number of the gear is 3 minus the fixed 1. And also we have two revolute joint with the degrees of constraint that is 2. Minus, we have to define the degrees of constraint for the gears if it's only 1. And then we can generate the result is 1. So I know that it's difficult to explain why there is 2 degrees of freedom between a gears. Directly thinking that is only 1 degrees of freedom. But we have to make that to fit the definition for our equation. That is, we can generate a final result with feasible degrees of freedom. Is that okay? Okay, thank you.
Great, thank you. And one more question, actually, your second slide, you show a very interesting mechanism, but you did not explain. Maybe you can say a little bit words regarding to this. I remember it's the second slide.
The second slide. The ancient, or this one?
Well, no, the next one.
Next one, okay.
The fourth slide.
The first slide.
The fourth slide.
First, this one?
Yeah, this Leonardo da Vinci's design, gear design. What they do actually? They look very complex.
Okay, that is
Next.
because there is the clockwork spring. And as we know, once we warm it up, the torque is stronger. But once it releases, the torque will become, the torque is decreased. And how about this one? That is a gear with a specific path. So how about that? If we have a stronger torque, but we set the arm, we set a shorter distance, and then they can make the force output become the constant. Once we have a stronger torque, but we have a short distance, and once the torque is become decreased, and then we have a longer distance, so the force output will become the constant. That is the design by Leonardo da Vinci.
Oh, interesting. Thank you.
Okay, thank you. Any more? Okay.
Wait. Okay, so I'm wondering that if when we design some structure, then there is some unnecessary and redundant degree of freedom.
Mm-hmm.
And so how can we avoid or find this redundant degree of freedom, and then so we can optimize our structure?
Well, I think it's at the first step of the analyze. That is, once we analyze the existing design, generally they won't have the redundant degrees of freedom, because if that is a product, if it is already, it can work, and generally they don't have. And if we follow the same characteristic as the design requirement and the limitation, I think we will have the similar result, but also don't have the redundant degrees of freedom. Okay.
Okay, so let's thank Professor Chen again So that's for today's lecture. And Professor Yongchen, thank you so much for joining us again.
Great, thank you. I enjoyed it. Thank you.
Yeah. So see you next week.
Yep, bye.
Okay, bye bye.
See you next week. Bye.